Hello everybody. Welcome to this training on neural network and deep learning. This series of discussions will revolve around one of the very popular concepts these days, which is neural networks, and then subsequently we'll also talk about how simple neural networks translate into something that is called deep learning or deep neural nets. But before going into those intricacies about neural networks, we'll do some introduction. So by way of introduction about myself, I am Arindam, and I have about 12 years of experience in data science. I've been practicing data science for about 12 years now, and I am a data science enthusiast and very keen on learning data science, and as well as helping others learn some of the techniques that I am conversant with as well. So what I want to do with this series of trainings is talk about neural networks in a slightly different way than what we typically see in some of the learning resources available about neural networks and deep learning. So we'll talk about that in due course. In terms of what to expect from this series of trainings, or what will be the structure of the content will look like. So if you have already gone through my training on natural language processing, which is available in YouTube in the channel Data Science Cafe, then you're already aware of the structure that I follow. So I'll be following the similar structure for this. In case you are new to my trainings, the structure that I typically follow is I do a theoretical discussion, a conceptual discussion about the topics, and then follow it up with some hands-on implementation. So no exceptions here as well. So that is the structure that I'm going to follow. And in terms of what to expect from this training, so this is going to be a blend of both concept build up, some of the conceptual aspects of neural network and deep learning, as well as implementation of those concepts using Python. And we'll start off from the very basics in terms of how neural nets are constructed and why they look the way they look like. And then we'll move on to discuss some of the most fundamental forms of neural networks, which we call the feed-forward neural nets or the multi-layer perceptron networks, and do a little bit of hands-on about that, and also understand how neural nets are trained, how the training of neural networks are done using Python. And then we'll talk about some of the more sophisticated networks like recurrent neural networks or RNN. We'll talk about long short-term memory networks, which are often called LSTM, and we'll talk about convolutional neural networks, CNNs, and then towards the end we'll also discuss about how transfer learning is used in the context of neural networks and deep learning. So that's a long list and a long way to go, but first things first, we will start off with the introduction first. In terms of the prerequisites for this training, so the prerequisites are very basic. So you should be familiar with the basic concepts of supervised learning. That is something that we will use on and off. And basic mathematics at undergraduate level, that should be fine to understand some of the conceptual aspects. And since we will be doing some of the hands-on implementations using Python, it would be good if you are familiar with Python to a certain extent, to the extent that at least you can install some of the Python packages and then work with those packages. But don't worry, if you are not conversing with Python, that's perfectly fine. You can still get along with this series of discussions. Skip the hands-on part maybe for now, and then in due course of time, as and when you learn Python, you can again return back and look at the hands-on implementation. So the Python part is only required for the hands-on implementation. If you are not conversant with Python, you can still move along. Okay, so and in terms of what is the typical target audience for this kind of a training, who will benefit the most? So obviously, if you are an aspiring data scientist, you will by the end of this series, you will be having a very thorough understanding of how neural nets work and know how to implement them. And also, if you are a practicing data scientist but you haven't worked extensively with neural networks, you will also benefit from the series of discussions. And but by the end of the series, you will be having a very firm understanding of the basic concepts of neural networks, which is very important to know, and you'll also know how to implement them using Python, some of the Python libraries, Python packages that we will use, and more importantly, you will have a very firm foundation about the neural net concepts, which will help you understand any new kind of network that you are studying, because neural nets are one of the very fast evolving areas. New kind of networks are coming up almost every year. So what I'll try to do is create a foundation through the training which is firm enough for you to understand some of the subsequent or some of the more sophisticated networks which are coming up these days. Okay, so that was a pretty long introduction, but I hope it was worth it because it sets the stage for the series of trainings. So we will now move on to the first topic of this series, which is concept build-up for neural nets. So intuitively, we will understand why the neural nets look like the way they look like and how they are constructed, starting from the very fundamental building blocks. Now, if you talk about neural networks and particularly listen to some of the critics, one of the most talked about criticism is that neural nets are black boxes. So you have a set of information you feed into a machine, and then there are some high computing algorithm which happens. The network gets trained, and then you get the output. Quite more often than not, you get a desired output. But then what happens in the algorithm is not always very clear. It's almost inexplicable. So that's often the notion about neural network. Now, what I aim to do right at the beginning is to break that myth. So neural nets are not black boxes at all. Uh, there are uh, there are fundamental components, building blocks of the neural nets, and it's very much possible to understand the nuts and the bolts of those components. So what it requires is just a little bit of patience to start from the scratch and understand why neural nets look like the way they look like. And that is what when I was and that was long back when I was trying to understand how neural nets work. This is something this is something which I was looking for, but I missed it because most neural net trainings which I tried to go through, they start off with something like this, where right at the onset you see a very complicated diagram, and then you're almost on the verge of becoming clueless that what is happening out here. And if at all it is not starting with a complicated diagram like this, then it starts with a code editor, be it R, be it Python, wherein straight away you're implementing some of the networks using some machine learning libraries without even discussing the basic fundamentals at length. Now, and then that is what I was alluding to when I was giving the introduction, that I myself felt that the blend of the initial concept build up and the implementation part is so very important when it comes to a topic like this. So And then as you move along, things really get complicated because neural nets, there are many variants of them, and each variant has been designed with a particular purpose in mind. But if you know the fundamentals of it, if the basics are clear, then understanding each of these variants becomes a lot more easier than if you start off just by assuming that neural net looks they have a certain kind of a representation, or if you straight away jump into the implementation using Python or R. So that's again one of the reasons why it's important to understand the basics, because otherwise what happens is, as you move into more understanding more complex networks, it becomes all the more difficult. So we will start off by understanding the most fundamental building block, or the most fundamental unit of a neural network, and that is called perceptrons. Okay, and perceptrons, by the way, concept-wise, they're not something very new. So the concept of perceptrons dates back to the 50s, 1950s, and the gentleman, a mathematician called Rosenblatt, who actually first came up with this concept of perceptrons, which are nothing but decision making units. So a perceptron will typically get some information from different sources, and then it will combine those information to make some decisions. Now that might sound cryptic, but don't worry, we will look at an example soon so that it doesn't sound cryptic. So let us straight away go to an example to understand what a perceptron is, which I just said is the most fundamental or the basic building block of a neural network. So this is how a typical perceptron will look like. A typical perceptron will have information flowing in from different sources. So in this case, we are assuming that there are three sources of information, and I'm denoting them by x1, x2, and x3. And they're flowing in to a system which is a decision making system, and this system is actually combining these three information and then giving me an output which is actually the decision that I want to make. Now let me illustrate the example now. So let's say there is a food festival happening in the town, and you're actually contemplating that whether or not you want to go this evening, and assume that this is your last chance to visit. So in order to decide whether or not you want to go to the food festival, there are three options, there are three questions or three deciding factors that you are considering. The first deciding factor is about the weather. So how will be the weather be? There are some meta-phase forecasts for rain, so you're very skeptical about that. So you want to be very sure that the weather is acceptable. The second condition that you're looking at is what kind of company will you have? Will you be accompanied by your girlfriend, boyfriend, or fiance? So that's the second deciding factor for you. And the third one is if you drive to the venue, will you have a parking space nearby? So these are the three factors on which you're trying to find out information, and basis this you will decide whether or not you will go to the food festival. So classic problem of decision making. And now if I replace your decision making unit, which is which is your mind, human brain, if I replace that by a perceptron, then what is happening is, this perceptron is receiving three sources of information, it's combining them in a certain way, and then it is giving the output, and the output here will be a binary decision, yes no kind of a decision. In this case it is whether or not you want to go to the food festival this evening, right? So that is the kind of scenario through which we will try and understand what how perceptrons make decisions. And at this stage, I think I can also draw an analogy. This kind of decisioning units fundamental decisioning units. Some of you would have seen, if you are familiar with the concept of logic gates, the which are the fundamental building blocks of any decisioning systems when it comes to circuit diagrams, right? So if you are aware of the logic gates, the fundamental logic gates and or etc., the logic gates also pretty much function in this way, right? So they receive signals, or they receive information from different sources, and then depending on the nature of the logic gate, they combine the information and give an output. So in a way, perceptrons also function in that way, but then it's not exactly the same. There are some differences, and consciously I brought in the analogy of logic gates here, because at a later stage we will see that there are some commonalities with how perceptrons and neural networks work, commonalities with logic gates, and there are some subtle differences as well. So park that thought for the time being, but I just wanted to draw that analogy at this stage. Okay, so moving on. So how does the perceptron really make a decision? So I said that the perceptron combines the information that it's receiving, and then it is based on that combined information, it is making a decision. So what it is doing is, so if I assume that there are p such factors, or p such pieces of information which the perceptron is receiving, and I denote those factors which influence the decision by x. So x1, x2, xp, there are p such factors or p such features, whatever way you may want to call them, on which the perceptron is receiving some information. So in the example that we were looking at, so in that example p was equals to 3. So there were 3 different types of information which were flowing in, and it was influencing your decision to go or not to go for the food festival, right? So if there are p of these x's, what the perceptron does is it basically applies a linear combination of the x's using some weights wi, and then it sums it up, and then there is a thresholding factor called b, and what it will do is it will compare this linear combination of x's and the w's with b, and if it is less than b, then the decision will be 1, and in this case you can code 1 as maybe if your decision is favorable, that you want to go to the food festival, and it is 0 if it is if your decision is if you don't want to go. So if we define the output decisions as 1 and 0 in that way, then the way the perceptron makes a decision is, if this summation is less than equal to b, then it says 1, and if this summation is more than b, then it says 0. Now, of these equations which are written over here, the x's are something which are known, right? Because these are the features on which the information is flowing in. The w and the b, these are the things which are unknown. So these have to be somehow estimated so that the decision making can happen. For the time being, we'll park the estimation part. We'll look at it at a later stage, but for the time being we'll assume that this is how the perceptrons work, and if you are already having questions in your mind about that, what is the guarantee that this kind of a decision making actually works, it makes good decisions. uh, so I was, as I was mentioning in the beginning, that this concept of perceptrons actually dates back to the 50s, and it was proposed by a gentleman called Rosenblatt. So he actually went on to provide a couple of proofs, and he published them as papers, that this form of this mathematical form of perceptrons is actually very useful in this kind of decision making, and he proved it that with a proper choice of w and b, perceptrons can make very good decisions. So I'm not going into those details of the theory because it's not necessary to understand to that extent. But then if you are really interested to know about it, you can look at you can do a search in Google and look at the piece of work done by Rosenblatt where he actually proves mathematically that this kind of a function uh, or this kind of a mathematical form can be very useful in decision making. Okay, so coming back to our example that we were looking at. So in our example, we had three influencing factors, right? And we'll call them as x1, x2, and x3. So and these x1, x2, and x3 were factors like x1 was weather, x2 was whether or not you will have good company, and x3 was whether or not there is parking space near the venue. So these were the three factors, and obviously then we will have three weights. So in the decision making here will happen like this. So if you go for the food festival, if you see that the linear combination of the w's and the x's are less than equal to b, and you ditch the idea if it is more than b, obviously w's and b's are something which have to be estimated. Now for the moment, instead of taking all the making all the hard work of estimating the w's and b's, let us say we assume some values and see that how the decisioning unit actually works. Okay, so this is the decisioning rules which we were looking at. Now let's say the x's or the influencing factors, uh, we code them as binary factors 1 or 0. So each of these x1, x2, or x3 will either be 1 or 0 depending on what kind of information you are getting. So for example, x2 was the factor whether or not you will be accompanied by your fiance, girlfriend, or boyfriend. So if x2 is 1, so we'll say x2 is 1 if you are being accompanied by these people, or if you are not being accompanied by these people, then x2 we will code that as 0. So generally when we define binary variables, we what we do is the favorable outcome is coded as 1 and the not favorable outcome is coded as 0. That's just a matter of convention, can be done the other way around as well. So in this case we are saying that if you have good company, then we will code it as 1, or otherwise we'll code it as 0. So no generalization intended. Of course I'm not trying to force upon the concept that the company of your fiance or girlfriend or boyfriend will always be a favorable outcome, but for this case, to avoid any controversy, we will just assume it to be that way. Okay, so so that is how we will code x1, x2, and x3. If we have a favorable outcome from x1, x2, x3, we will call them as 1. If the outcome is not favorable, we'll call them as 0. So for example, with x1 also, if the weather is not favorable, we'll call it as 0. If the weather is favorable, we will call it as 1, so on and so forth. Okay, so that is how the x's are coded. Now as I was saying, the w's and the b's are something which has to be estimated. So instead of estimating them, let's choose some values of w and b for the time being, right? Just to get the understanding right. So if we say choose, let's say w1 as 6, w2 as 2, w3 as 2 as well, and then b as 5, then let's see how the things look like, right? So and there will be many possible combinations of x1, x2, x3 that they take values 1 and 0. So there will be many different combinations, of which we are looking at four such combinations. Okay, and these four combinations are what kind of combinations? So these are the cases where x1 is always 1 and x2 and x3 are taking their all possible values. So x1 is always 1, x2 and x3 are taking values 0, 0, 1, 0, 0, 1, and 1, 1, right? And then what are we doing? We are basically computing this linear combinations, and we are calling the linear combination itself as Z, and we'll compare Z with B and then see what the decision comes out to be. So for these four cases and for this kind of choice of W and B, you see, as long as x1 is 1, and because the weight of x1 is 6, which is significantly higher than the weight of the other factors, as long x1 is 1, regardless of whatever values x2 or x3 take, uh, the linear combination which you are denoting here by Z is always greater than B, and hence your decision is yes. So I think there is a typo out here. So is there a typo? No, there's not a typo. Sorry, that's correct. So if the decision is yeah, so since the value of Z almost always, not almost always, in fact always exceeds B in this case, for this particular four cases, the decision is yes. So you want to go to the food festival. So if I translate this into plain English, for this particular choice of W's and B's, what happens is, irrespective of what x2 and x3 are, or irrespective of whether or not you have parking, or irrespective of whether or not you are having good company, if the weather is fine, right, then you will go. So it appears as if the weather is the single most important factor. And why it is that way? Because we have chosen the weights to be that way. Had the weights been chosen differently, the decision outcomes will also be different. So we'll look at another example that will make things clear. So in this case, we are slightly changing the choice of weights. So instead of taking the previous sets, we are now making B to be 3. W1 is 6, W2 and W3 also remain at 2. So, and we are looking at many other combinations as well. So these are the first four cases we looked at, where we saw that irrespective of the value of x2 or x3, as long as x1 is 1, the decision is always yes. Now, if I look at the last four cases where obviously x1 is 0, right? So x2, x3 are taking their respective values, and what we see is that if x1 is 0, then again, if you compute the linear combination, do some simple math, you will see that as long as x1 is 0, the only way by which your final decision will come out to be yes is if both x2 and x3 are 1. Again, translating that into plain English, what that turns out to be is if the weather is not favorable, then the only way you are going to decide that you will go to the food festival is if both the conditions are satisfied. One, you have good company, so your fiance or your boyfriend or girlfriend is accompanying you, and there is parking space near to the venue. So if both these conditions are satisfied, only then you will go to the food festival if the weather factor is not favorable. For any other combination, in the last four cases, you see the decision is no, and that is again driven by this particular choice of W's and B's. So essentially, what we see here is that as you are changing the W's and the B's, the values of W's and the B's, the decisioning model itself is changing, right? Now here we looked at two particular choices of W's and B's to understand how the decisioning system actually works. But then in order to ensure that the decision that you're making is the right decision, there is some training, there is where the training of the algorithm is involved, right? So the algorithm has to be trained to estimate the weights in such a way that the decision you are taking is the right decision. And then there comes other intricacies, like how do you define the decision to be a right decision? How do you measure error? So we'll go into those concepts in due course. So what thus far what we have done is we have just explained that as far as neural nets are concerned, what are the most fundamental building blocks of neural nets? So neural nets do decision making. Their most fundamental building blocks are perceptrons, which also do decision making. how do perceptrons make decision making, how do they look like, how do they combine information to arrive at a final decision. That is what we discussed. Now, three key takeaways from what we discussed so far and what we will be using as concepts into the further discussions as well. So perceptrons, they provide a very simple and effective way of combining different observed factors, and then they can help arrive at a decision. So if there are a lot of factors which is influencing the decision, perceptrons can actually combine them to help arrive at a decision. How the features are combined and how the decisioning model actually works, it depends on the choice of weights W and P. In this case, we took some examples and have seen that how the choice impacts the decision making. And the last point is a very important point. So if we see that a single perceptron can do simple decisioning tasks like the one that we were looking at, the example that we were looking at. If a single perceptron can do simple decisioning tasks, then intuitively it seems quite logical that for more complex or complicated decision making tasks, if we can build a collection of perceptrons or a system of perceptrons, that will be effective in doing more complex decision making. So I'll reiterate this point once again because this is the key point which gives rise to the structure of the neural network. So we have seen that a single perceptron can receive multiple information, combine them and do a decision making. And if that be the case, then for more complicated, more complex decision making, it seems intuitive and logical that if we combine a collection of perceptrons, arrange them in a certain way, together they can do more complex decision making. So, and we will see in the next video how this very simple looking perceptrons can be combined together when it comes to doing more complex decision making, and this way of combining perceptrons, how it actually eventually leads to the structure of the most basic form of neural networks. Okay, so that's all for this video. So we have done the basic introduction of perceptrons and how they work. In the next video, we'll look at how perceptrons are combined to give rise to what we call neural networks. Thank you for watching. Stay tuned for the next video. Bye.